Alrighty, can you guys hear me all right? Everything working? Testing? Testing, stream happening, whether I like it or not. Testing. Yeah, just hanging out for a bit before we start the stream. The problems today were pretty hard, I'll be honest. For those of you who have not been to one of these streams before, I am following a online University of Chicago GRE Prep, and this week's problems, at least the first half, were quite difficult for me. So that combined with some personal stuff took extra time to finish them. But the standard stream schedule will be Monday, Friday. this week was just a nightmare for me to navigate. So we're streaming on Wednesday. I don't want to deprive us of content or set myself off schedule because we're trying to do 1 week a week. But anyway, we will be getting started here just in a minute. I guess I should have my little funny graphic up that I worked so hard to do in 2 minutes. But yeah, we will be getting started here shortly. I'm going to try and move towards like, I guess like monetizing the stream a little bit and doing some like widgets and stuff to get more viewer interaction while I do this. I want to be a little more lively. I know math can be slow paced, and I think we can make the streams a little more fun. But for the time being, I'm just going to incrementally add stuff in, like that opening graphic you saw. And I might make a closing graphic at some point, but I didn't have time to this morning. But yeah, I think we'll just chill and talk for a few minutes, and then I'll get started maybe 11:15, 11:20. Everybody cool with that? Cool with that? I can link the GRE study thing in the chat so that when we get started, you guys can follow along and see what problem I'm working on and maybe work ahead if you are smarter than I. Here is the link. It's Math University of Chicago. We're going to be following this week by week. So every Monday I'll do the first 11 problems, or in this case Wednesday, and every Friday I will be doing the second 11 problems for each week. And they have practiced exams on the website as well. So maybe when I'm done with all the weeks, if I feel confident, I will try and take some of those exams live and just see how terrible it is for me to do. But ultimately, I'm just trying to keep myself sharp at math before I try to go on to graduate school and get my PhD. So these problems are really more to study than because the GRE is super important. Colleges have sort of like moved away from the GRE as like a qualifier for getting into grad school, as far as I've been able to tell. But, you know, so like I'm not really concerned about my score going in or anything like that. I'm just trying to make sure that I don't waste this year of opportunity and learn as much math as I can before going on to grad school, because for those of you who don't know my like personal journey with academics, I kind of like transferred from an mechanical engineering curriculum at Old Dominion University, which I took for 2 full years, like through sophomore curriculum. And then I took like a year off for COVID and transferred to Randolph College, where I met Michael. And then I finished my math degree in like 3 semesters. Well, really 2. I was not sure if I wanted to major in math the first semester, but took like intro to proofs and that's it. But yeah, so I'm kind of like on a cramped timeline for learning math. Sorry for my crumpled blanket. I try to keep the space clean, but didn't throw that out of frame yet. But yeah, so I transferred to Randolph and got my math degree rather quickly. So in terms of like, especially at the lower level math, I'm not like as strong theoretically as I would like to be. So this is a really good opportunity for me to like sharpen all my skills up so that when I go to grad school, I can apply them. Looks like we don't have a crazy amount of people in chat. That's all right. It's all good. But yeah, we'll be getting started here in just a moment. You know, maybe give it 5 more minutes. See if we get any more people. Looks like there were a few waiting for it to get started, but they left. They might be back. Yeah. How's it going, Adam? Welcome to the stream. I don't believe I've seen you here before. Thanks for stopping by. We are going to be starting in about 5 minutes. Right now I'm just talking to fill some time. Just hang out. And then we'll be getting started. Can you see the previous chat? Like before you joined? I linked the link to the problems we're going to be solving in the chat. So I might want to make a chat bot to like, I don't know how it works for YouTube. I've only streamed on Twitch before doing this stuff. So, but anyway, I might try to set up some chat commands and stuff for different social links and stuff like that, like for the problems. You can see it? Okay, that's good. Yeah, so that's what we're going to be doing. We're going to be starting with week 2 and doing the first 11 problems. I have prepared most of these, but frankly, if I didn't, the stream would have been like 12 hours. So I'm still getting there. Last week, especially second stream last week, was like quite easy, but this week I had problems. But it's, you know, I'm filling in gaps in my knowledge, so you can't be good at everything all at once. So moving forward. I'm actually not entirely sure what I want to research in grad school. I've done a few areas of like high level study. So for my what's undergraduate research paper I did on generalized Stokes theorem, which is pretty high level differential forms study, which culminated in a proof of generalized Stokes theorem, which kind of like generalizes a ton of super important calculus theorems. So that was really awesome. Following that, I did an independent study of algebraic topology, which I really enjoyed. I might want to go further into that because I only did that on like an 8-week study, and I don't feel like I got as much. Well, I mean, I did as much as I could for 8 weeks, but you know, I could further my study in that. As for grad school, like my focus for my study, I'm not entirely sure yet. I'm still kind of sorting through it. I haven't really found another subject that I want to dive into like that at that level, but you know, we'll see. Right, like I said, right now I'm more in like sharpening the basics of my toolkit than I am looking to deep dive into something else again. But you know, time will change that, I'm sure. I'm not sure what book we used for algebraic topology. I could pull it up. I don't know. It's not even been that long. I just can't remember. I'm terrible with names to begin with, so you have my apologies for that. Although I will say that name doesn't ring a bell, so probably not that book. No, I haven't even looked into vertex operator algebras at all. The previous like channel editors or channel editor Noah, and I think he had one other student on. They did a summer research project with him on vertex operator algebras, but I have not even begun to look into those aside from a single lecture he gave during senior seminar about them. So I have like an extremely bare bones knowledge. In fact, in terms of like my knowledge of mathematics, algebras is probably my weakest point. So it'd be pretty hard. Do I know what a scheme is? No. I don't even know what you're asking. My bad. My bad. Yeah, we're gonna start here in 2 minutes. So you don't have to wait forever. Don't want to lollygag around, but I think taking this time at the beginning just to talk is probably good for the stream, right? Get to know me. I haven't been around too long, so get to know my personality a little bit. Algebraic geometry. Yeah, no, definitely not. I've not encountered the term in my study yet. We are pretty low on viewers today. But that's all right. That is all right. Less stress for me. Yeah, I chose 11 o'clock today because we have this analysis for the main channel that tells us like when the most people are online, and I think 11 o'clock was the optimal stream time. And you don't have one for this channel yet, but I figured there's a lot of crossover. But it seems like I got the most viewership when I streamed at like 1 o'clock, so maybe I'll try that on Friday. We'll see. I don't know. For those in chat, what time, I'm talking about Eastern time, but what time like works best for you to be out to watch the stream? Ooh. I think sitting down for a stream is different than watching a video, though. Because when you sit down for a stream, it's like for the long haul, and when you watch a quick video, I don't know if the analytics are the same, is what I'm trying to say. 4 p.m. there. Okay. Yeah, I don't know. I don't know if the analytics are skewed for that reason, because people can be like online on their phone looking for videos to watch like on their lunch break between 11 and 1. But they might not sit down for a 2-hour stream, for example, because that's too long. So I'm not sure how accurate that is. But like I said, I'm going to add some like chat features, and I might make a bot that'll do polls and stuff, and maybe when we have good viewership I can like poll availability or something, or I might ping the Discord or something like that. I'm not sure. I'm still adding functionality to the stream. We're still kind of bare bones right now. Yeah, I'm super trying to review. The way an engineer approaches math and the way a mathematician approaches math are just not at all the same thing. I think the math GRE encompasses pretty much every class you would consider like essential for like a math undergraduate degree. So like everything from like, I mean, I would say calculus 1, but like that doesn't really matter. Like calc, abstract algebra, linear algebra, real analysis, some topology questions. There's what else have I done on? There's like some statistical analysis, combinatorics type problems. Just kind of a little bit of everything, really. Yeah, there's abstract algebra, yeah. All right. I think we've talked enough. I'm going to get started. I will still answer questions on to the chat, but I won't have as much time to look at it because I'll be doing math. So if I miss your question, I apologize. Hopefully somebody in the chat can help you if it's like a math question, but I am going to go ahead and get started. So let me get my window capture open and I can show you guys the first problem. Alrighty. Did you guys hear that? Alrighty. So we've got, here's the first question. I'm going to try not to block the math with my face also. I have been horrible with that lately, but we're going to try and improve. So this first question here is find the coefficient of y cubed x to the 6th power in that expression there. So basically this is an expansion problem. Well, not basically, it is an expansion problem. So you need to find a way that's not extremely time consuming to multiply these out and to locate the coefficient. There are a few ways to do this. There's like a binomial expansion formula that you can use. But I expanded using Pascal's triangle. I don't know if any of you are familiar with expanding binomials with Pascal's triangle. And there's actually a trinomial triangle as well. But I find that particularly easy to follow. So I'm not going to write out all these terms because it's just obnoxious to do. I'm just going to show you the triangle and kind of like go through how you write out terms using the triangle. And then I will tell you the answer. But if you want to on your own, you can try using the formula maybe and use a different method than I did. But I will just show you the Pascal's triangle method, and I'll just show you with the binomial just for the sake of it. But the trinomial triangle is similar in methodology. So let me get the triangle up here because I certainly don't have that memorized, even though it's not that difficult to produce on your own. It will be faster for me to write it. So let me get this off. Let's see. I closed that tab. I certainly hope not. Oh, there it is. Alrighty. Yeah, forgive any clunkiness the stream has. My desk is very crowded and it's also massive. Got a bunch of stuff set up right here. I'm thinking about potentially buying a desk and making an entire recording studio, but for now I have this built-in desk in my house and it's in my living room and it's not really ideal. Also, the overhead light is on, and if you've checked out my previous 2 streams, it will randomly turn on and off, and it decides when it wants to be on. I have tried changing the light bulb. That is not the problem. I think the wiring is just loose and it doesn't work. And I've had an electrician over here 3 days, and of course it stopped working consistently right after he was done doing the work here. So, you know, can't have it easy, right? Anyway, let me write you out Pascal's triangle for the 7th power. So basically you start with a 1. I guess I'll just make this whole page. See if I can write this neat for you. You start with a 1, and on each part of the triangle on the edges is going to be 1s. Here, let me make this as pretty as I can. So then when you're in the middle, you add the 2 things on either side of it. So there's 2, and then you put 1s on either side. And then, so we go down 1 row, and we add the things on either side here. So that's going to be 3 because it's 1 plus 2. And then it's going to be another 3 because 1 plus 2. And then 4, 1. And for the record, this is row 0, not row 1. So you actually need to make 8 rows. So that's 4. That's going to be 6. Let's see if I can actually do math. This is the hardest part of streaming, is doing the arithmetic. You got 5, 10, 10, 5, and then we got 1s. And you'll see this is symmetrical. What row is that? This is row 1, 2, 3, 4, 5. So we need 2 more rows. We add 1s here. We've got 6, 15, 20, 15, 6, and 1. And then this will be our last row. We got 1s. We have 7, 21, 35, 35 again, and then 21, 7, and 1. So these, did I block it? No, I think it fits in there perfectly, right? That 1 is the last thing I wrote. Yeah, so this is the triangle, and each of these numbers represent the coefficients. So if you have, this is, say we have like in a plus b to the 7th here. We use this triangle. And because addition is commutative, it doesn't really matter like which numbers, which coefficient. Also, it's symmetrical. But this will be the coefficient for the first term. So this will be like a. This will be a to the 7th. And this will be plus, and that's times b to the 0 power, which is just 1. But it's worth noting because, oh, well, that's actually a little off screen for you. Let me scroll down just a hair. Can I do that? No, unfortunately not. Let me see. I can just write it up here, I guess. So let's go up this way. Just for example, we'll have a to the 7th times b to the 0. That's the first coefficient. And then this 7 will be the coefficient for the next term, but we are counting down with the a's and up with the b's. So we'll have plus 7a to the 6th, b to the 1st. And then the next one will be plus 21a to the 5th, b squared, etc. And you just keep going and counting down with the a's and up with the b's. And make sure that you don't mess it up when they pass each other. But other than that, it's pretty straightforward. It's not very difficult. So this is how you expand a binomial with Pascal's triangle. And I find this to be particularly easy because really all you have to do is do the arithmetic for the triangle. I'm going to check chat real quick. Make sure we're following along. Oh, Michael's here. Hi, Michael. Yeah, so that's how you expand binomials using Pascal's triangle. And like I said, there is a trinomial triangle that is similar, but I'm not going to go over it just for the sake of time. But know that it's asking for the coefficient of a specific term. Let me check real quick to see which one. It is asking for the coefficient of y cubed x to the 6th. So you would add up all the terms that have a y cubed x to the 6th in it, and you're going to find that they're 840 exactly. And that is answer choice B. So that is the first one. Are there any questions about that? I feel like it's pretty straightforward. Pretty straightforward indeed. Pascal's triangle is cool. I had never used it. I'd seen people using Pascal's triangle, but I personally hadn't used it until this problem. But I was familiar with the binomial formula, expansion formula, but that's not as fun as using a triangle, right? Any questions before I move on, briefly? Yeah, use latex, exactly. Yeah, I mean, this is supposed to be like for a test. Obviously, you can't use latex for a test. But, yeah, I mean, if you're just solving problems on your own time, I recommend highly just plugging it in because that's easier. Alrighty, I don't think we have any questions, so I'm going to go ahead and move on. The next question is an integral, and it is a gnarly integral. Hold on, my stream playback is so far behind. Okay, there we go. Now I'm caught up. I don't know why it was. It was like 7 minutes behind what's live, which is not particularly helpful for me. Okay, so let me show you this next problem. So we have, we're trying to find which of the following is closest to the value of this integral. Now this integral does diverge. It can't be evaluated completely, unfortunately for us. But I am going to have a rather complex method to bound it so that we can estimate the value with a good high degree of accuracy. As you can see from our answer choices, we don't have a lot of wiggle room in terms of inaccuracy with our estimation. So I'm going to do some cool integral stuff, hopefully not mess it up, and see if we can't get this thing knocked out. So first off, the method we're going to be using to evaluate the part of the integral that we can evaluate is we're going to find the inverse function, which is rather straightforward. And then, let's see. I'm going to find our inverse function. Sorry, I need to put the, silly me. You need to see what I'm writing, right? I need to find the inverse function and the integral will be equal to where that intersects the line y equals 1. So our original integral is equal to the integral where the function intersects the line y equals 1 of the inverse function. So first let's find our inverse function. Our original function, if I can do this from memory, which I don't even know if I can, let's see, this is our original integral, so I guess I should write that down. 0 to 1 of the square root of 1 plus 1 over 3x. That's our original function, dx. So to find the inverse function, we are going to, I believe you plug in x for y and then you solve for y again. So we're going to set y equal to this. And to find the inverse function, you swap your variables and then solve. So, yeah, I should write this as f of x actually. So it's clear that we're taking an inverse here. So then we have x equals, this is the f inverse of x, plus 1 over 3y. And so we can square both sides here to get x squared is equal to 1 plus 1 over 3y, which will give us x squared minus 1 is equal to 1 over 3y, and then we can flip both sides to find that y is equal to, let's see, that'll be 1 over 3 times x squared minus 1. Hold on. Let's make this equal sign a little prettier. So that is our inverse function. That is equal to f inverse of x. So now we want to so to be clear, let me just kind of reiterate what we're about to do here. The integral, the original integral, if we set this equal to I, is equal to x naught plus the integral from x naught to infinity of, I probably should have written this before, the inverse function of x dx, where x naught is the intersection point between the inverse function and y equals 1. Can you shorthand between? Can you even see that? I'm sorry. And y, I'm running out of room, equals 1. This is not my best handwriting, I'll be honest. For those of you who've watched my previous streams, you know my handwriting usually gets worse with as the stream goes. So we're in for it this stream. Okay, does that make sense? I'm sorry if it doesn't. I did not deliver it very clearly, did I? What tool am I using? I am using GoodNotes is the app I'm using to write, and I'm using an iPad to write my math. So that's what I'm using. Alrighty, so we have that set up. To find our x naught, we just need to plug in y equals 1 and solve. So let's go ahead and do that on the next screen, I guess. Not next page. I can move my face cam back down now that I'm not writing like all in the margins. I have it cut off like this so I take up the least amount of space. You can only see my head. Alrighty, so let's see. If we were to plug in 1, we will have 1 equals 1 over 3 times the square root of x minus, not square root, just 3 times x minus 1. X squared minus 1. So we can multiply by 3 to get 3 is equal to 1 over x squared minus 1. And then we can flip both of those to get 1/3 is equal to x squared minus 1. We can add 1 to both sides, and get 4/3 is equal to x squared, which means that our x naught is equal to the 2 over the square root of 3. So remember, by our formula, our integral is equal to x naught plus the integral from x naught to infinity of f inverse x dx. So now we have our bounds of integration, and we have our term that we need to add here. And we're going to do this so we can integrate out as much as we possibly can, so that we can bound our function with what we can get for the answer. For the GRE, I mean, normally for these types of problems, you could use like a summation estimation or something like that. But I think that this kind of method is probably a good method to know for evaluating the integral, because it is very useful for divergent integrals. So let's set up this integral that we've just written here with our formula now that we've solved. So that's going to give us 2 over the square root of 3 plus the integral from 2 over the square root of 3 to infinity of, what was our inverse again? Yes, 1 over 3 times x. I guess we can just pull out that third, so let me just do that. Save ourselves some time, right? X squared minus 1, and then put this 1/3 out front because we can pull it out as it's a constant. From here, this is I, our integral value. Did I write 1? Oh, that was for the other thing, yeah. So from here, how many of you guys know what we can do to easily manipulate this for a trig definition? You recommend Miro for this. I've never heard of Miro. I can check it out though. Thank you. If you factor out a -1 here, we can see that this is equal to 2 over square root of 3 plus, minus, 1/3 integral from 2 over root 3 to infinity of 1 over 1 minus x squared dx. And this, if I remember correctly, is the antiderivative of the inverse hyperbolic tangent, like that. So that allows us to integrate that right away. Sorry. So that gives us, let's see, we will have 2 over square root of 3. I guess plus the limit as n goes to infinity. We have to take a limit because of that infinity there, of -1/3 times the inverse hyperbolic tangent of x, and this will be from 2 over square root of 3 to n, as we have written our n there for our limit. Now we can now substitute in the equivalent definition for inverse hyperbolic tangent here, which is, so I guess I'll write that on the side. I think I have room here. So tan h of x is equal to the natural log of 1 plus x over 1 minus x. So we are going to make that substitution. Oh, it's 1/2. I'm sorry. 1/2 times the natural log. That is an important 1/2. So let's go ahead and make that substitution. And before we move on to our next page, so we have 2 over square root of 3. Keep our limit here. That's not. N goes to infinity. And we are going to combine this to a -1/6. Actually, let's go ahead and combine steps here just for the sake of saving paper. we will have 1/6, and we are just going to, by logarithm rules, flip that fraction there in the natural log. So we'll have 1/6 times the natural log of 1 minus x over 1 plus x from 2 over square root of 3 to infinity. So that's what we have now. And now we're going to evaluate the part of our integral that is defined here and use that to bound our integral on either side and rule out some answer choices so we can finish. Did I miss a dx? I don't think I missed a dx. I missed a dx here. Maybe that was just an earlier comment, but yeah. All right, so let's go on to the next page and do that. Our go ahead and substitute in. No, looks like I missed erasing this. There, you guys can barely see that. Were you able to see this? Oops. Yeah, okay. I'm just trying to get a... You couldn't see the natural log thing. Well, I verbally said it and wrote it down here. Anyway, so we're going to evaluate the part of our integral that is defined right now. So the part of our integral that is defined, I guess like the defined part, oops, we're going to have 2 over the square root of 3 from our x naught, and that is going to be, let's go ahead and just write it out. It will be the plus 1 over, well, I'll just do an over 6 over our term here. The natural log of 1 minus x over 1 plus x, right? Because we flipped it, yes. And then that will be all over 6. Oh, I was substituting in. So it'll be 1 minus 2 over root 3. Let's just rewrite this here so it's nicer looking. We'll have 1 minus 2 over the square root of 3 over 1 plus 2 over the square root of 3. And that will all be over 6. It's kind of an ugly looking thing. So let's see if we can simplify what is in our natural log. And we're going to do that by multiplying both sides by, or top and bottom by 1, which we're going to write as 1 minus 2 over square root of 3 over 1 minus 2 over square root of 3. I believe that's the right version of 1. So what will that give us? Well, let's see. We will have, what will this term equal here? We'll have 1 minus 4 over square root of 3 plus 4 over 3, right? And this is the, you gotta write our log in there. Well, I guess we're just writing what's inside. And then down here we will have 1, the middle terms will cancel, and that will be plus 4 over 3. Alrighty. Whew. And so 1 plus 4/3 is going to be equal to, this part down here is going to be equal to 7/3. Right, yes. Let me check my notes. I'm losing myself here. So, oh yeah. Wait. I'm losing myself here. And we can flip this up, right? So we'll get, this is still in the parentheses for the record. Still doing our margin notes here. We'll get 3 minus 12 over square root of 3 plus 4, right? And that's all over 7. And then this becomes 7 here. So we'll have 7 minus 12 over square root of 3 over 7. Is that right? Is that right? I think it's right. No, is it right? I feel like I messed up here. Somewhere. Oh, this should be negative. Because it's negative 2/3. Yeah. I dropped a negative. I dropped a negative. Did anybody point that out? Is the chat just yelling at me? Where's your negative? No. Anyway, this should be negative because we have a minus and a plus here. So that will make this here equal to negative 1 over 3, which means that we can flip just the 3 up, and that'll change that to a negative. So our denominator is completely cleared, which means we will have 3, I guess I'll just put the negative out front for now, 3 3 negatives out front. 3 minus 4 over square root of 3 plus 4, which is equal to 7 minus 4 over root 3. And that's in our natural log. So let's go ahead and rewrite all that we just did there. 2 over square root of 3 plus the natural log, I guess minus the natural log now because we have that negative out front, minus the natural log of 7 minus 4 over square root of 3 all over 6. Alrighty. Hi, Aaron. Let's see. So now we can take... So we know this fact. This is to bound our integral now. That 1.74 is greater than the square root of 3, and the square root of 3 is greater than 1.73. So that allows us to bound our integral in the following way. We will have 200 over 174 minus the natural log of 0.04. Just plugging in for that is greater than I, and then 200 over 173, 173 minus the natural log of 0.08 can be over 6, and we can wedge it in there. Now this can be written, this natural log here can be written as the natural log of, would that be 12, 12, oh, my face is in the way. Man, I told you, I'm not just gonna like slide out of frame. There we go. 12.5, and this can be written as the natural log of, I believe, 25. And if you evaluate that, you will find that our integral, the only answer choice we can choose for our integral is 1.6. So that's about the best approximation method I was able to find. Can you guys see all that? Does that make any sense? Have I lost anyone? Should be negative. Yeah, I brought the negative out. And yes, I just brought the negative out. You're right. There's a negative there. I just brought it out. It's it took this from here. This was a plus. I made it a minus right here just to make it. I mean, you're also correct. Not disagreeing with you. Yes, so 1.6 is our value there with that approximation. You can, explore that on your own if you want to find out what that means for you, but that gives us the only that is precise enough to land our answer at 1.6, which I believe is C, like leaning over to be in frame. Okay, so that is number 2, and now we'll move on to number 3, which is an interesting problem as I did this one fairly close to the end, and although I have programmed before, my brain just completely shut off. So I'm not even going to write number 3 out. Let me move me back in frame so you can see me. Move my head back in frame. Let me just get my window capture open for you guys and you can see what we're doing before I move on. So can you see that? Yes. Okay, so we have this algorithm right here. Where we have these nested while loops in this if condition. So we have iterating x's and y's that are going up until this if condition is met, which will stop us from iterating our s's, the output. So we want to know what the closest value to our s is going to be. So with this in mind, we can write our iteration process as a double integral. And I'm going to do that in polar coordinates because we have a circle here, or approximately a circle, I should say, because there's it only goes up by increments of 1. Whereas if we do an integral, we're going to consider everything. But we can write it as an integral in the following way. Let me get my iPad back up. Here we go. So what we have here is this right here. So we have, this is 1,000, and this is 1,000. This is our area D that we're integrating over. And I'm just going to write it as 4 times the integral because we're taking this full circle, but we can just write that as a product of the 4 of these wedges here. So we're going to have 4 times the double integral over this area D of x squared dA. Now, for those of you who don't remember polar coordinates, we will have that x is equal to r cosine theta, and that dA is equal to r dr d theta. So that gives us the following. We will have 4 times the integral from 0 to pi over 2 cosine theta times the integral from 0 to 1,000 of r cubed dr. And we can do that because we have the product of functions and their variables are separated. So evaluating those integrals is very easy. This cosine is going to be 0 because the integral of cosine is going to be sine, and then we will have, let's see, what would that be? Here, I'll just write it out. So the integral of cosine is going to be sine, so we'll have sine from 0 to 2 pi over 2, right? And that will give us, let's see, sine evaluated at pi over 2. Am I missing something? That's supposed to give us 0? Am I missing extremely basic math? Am I missing extremely basic math? Sine theta. Let me just write this properly before I continue brain farting. From 0 to pi over 2, right? And sine at pi over 2 is going to be 1, and sine at 0 is 0. So it's just, am I missing something? Am I dumb? Am I correct in saying that it's 1? I don't think it really matters. It doesn't. Oh, because it's 1 being multiplied. Oh, that's why it disappears. Yeah, I was just failing at basic mathematics. So this goes to 1, and then so we'll have, this one is going to be r to the 4th over 4 from 0 to 1,000. And then the 4's from this and this are going to cancel out, so then we'll have r to the 4th. And then we can write that when we plug in 1,000 as 10 to the 3. So r to the 4th, the 0 obviously contributes nothing, is equal to 10 to the 3rd, that's 1,000, to the 4th, which is equal to 10 to the 12th. Yes. I understand the difference between addition and multiplication. Yeah, so 10 to the 12th, and that is hopefully an answer choice. And it is indeed, that is going to be C. It's approximately the output. I thought I had turned my notifications off, but apparently not. They are off. What? How'd the text get through, man? I don't know. Do not disturb has failed me. So that is it for number 3. And now we have number 4. So let me flash that up on the screen for you. We are going to want to see which of the complex functions are holomorphic. We're going to do that using Cauchy-Riemann equations and some fancy derivatives that we will need to evaluate. So let me get that up for you. Alrighty, so we have these 3 functions here. We want to see which are holomorphic, which means we need Cauchy-Riemann equations, which I probably have to look up because even though I've used them recently, I don't remember. I'll just look them up in my notes. So let's get this window out of the way and I'll copy these down. We'll start with the first one. Well, actually here, let's use a strategy here. I feel like this is good. Let's see if there is a good one to start with that will eliminate the most answer choices. So let's see. We have our answer choices are 1 only, 2 only, 3 only, and 1 and 3. So 1 and 3 will be good to start with, as if we do those, we'll be able to potentially eliminate 2 answer choices. So we will start with 1. So the first one is f of z is equal to x plus sine x hyperbolic cosine of y plus I y plus cosine x. I can't even fit this on here. Hyperbolic sine y. So we need our Cauchy-Riemann equations. Let's see what those are. I believe I have them in my notes somewhere. Did I do them in the last one? I think the last notebook I have open is the last. Yes. So did I use these in the last 11 or not? Could somebody drop them in the chat just to save you some time if you know them? I don't even have chat open. I wrote normal cos. Yeah, I'll fix that in a second. Did I use them in this last one? I don't think I did. Does anybody know their Cauchy-Riemanns off the top of their head? Or is anyone better at memorizing stuff than me? Because I am not. Nope. Cauchy-Riemann. I have my notes within arm's reach, so give me 1 second. Actually, I can probably just Google it. That's faster, right? Cauchy-Riemann equations. Yeah, here we are. So we have du over dx equals dv dy, and I believe u is the real and v is the imaginary parts, right? Yes. Yeah. Yeah, v is imaginary. So with u real and v imaginary, that's the first one. And the other one is du dy is equal to negative dv dx. Yes. So let me fix, they said I made a mistake. So let me see. Hyperbolic cosine. Oh, you're right. I did write regular cosine. Thanks for catching that. That would have changed my answer quite a bit. And that is hyperbolic cosine of y. Alrighty. So let's start by taking the derivative, or the partial with respect to x of our real part. So let's see. So we'll have d over dx of f of x, or f of z, sorry. And we can see the x is just going to be 1 plus, and then we can consider that hyperbolic cosine of y as a coefficient because it's not with respect to x, and then just take the derivative with respect to x of sine of x, and that will give us cosine x hyperbolic cosine of y, and then we want to take the derivative of the imaginary part with respect to y. So can you guys still see okay if I write dy? Is that off screen? It's nearly. I'll try to make sure I stay on screen here. Of f of z. This is of the real, I should say the real part of f of z, and this is of the imaginary. And that's going to be equal to 1 once again, plus, what is the derivative of the hyperbolic sine? I do not know that off the top of my head. What is this test here? Let me link it to you. I'm following a GRE Prep, online GRE Prep from the University of Chicago that was published in 2019. They have, I believe, 6 weeks of problems that you can do. And it's been extremely helpful because these problems are very challenging, and it's helped me strengthen my weaknesses in mathematics across the board, as my math career has been pretty sporadic, and I feel like I haven't gotten a chance to delve in really deep on some of the like easy stuff, I guess. I don't mean to minimize math, it's not an easy subject, but the stuff I took when I was an engineer, I feel like I didn't learn as well as I could have. That being calculus 1 through 3. So like I'm more likely to screw up a basic chain rule problem than understand that I need to use Cauchy-Riemann equations for this complex analysis problem. Is anyone the derivative of hyperbolic sine is not oh, it might be hyperbolic cosine. Is that how it is? Let me just look this up really quickly. I might need a table for these. Let me see. Derivatives of hyperbolic functions. Oh, it is hyperbolic cosine. Okay, that works out for us then. So we'll have plus cosine x. I guess that's convenient. And hyperbolic cosine of y. So this first equation is verified here. So we can just like put a check, I guess. I will go ahead and erase this because that one was kind of like a trivial calculation anyway, and then verify the second one, and I'll do the next calculation on the next page. So this is for the second equation. So let's take the derivative with respect to y of the real part of f of z. And that is going to be equal to, well, that x is going to give us 0. And we are going to have, let's see, what is the derivative of hyperbolic cosine? It's just sine. Oh, there's no negatives. This is not very difficult. I was thinking it was going to be harder, but it's not. That's going to give us plus sine x times the hyperbolic sine of y. And then we will, let me make sure I don't cut this off dx of the imaginary part of f of z. And we want this to be negative what we have here, so we'll just pick up a negative sign, hopefully. So our y is going to go to 0, same thing as before. And we will have the derivative, and we will in fact. So we're going to pick up, it's not going to be a plus. We're going to pick up a minus because the derivative of cosine is a negative sign, minus negative sign of x, hyperbolic sine of y. So this satisfies both of our Cauchy-Riemann equations, and 1 is good. And let's write out our second function and try to verify that one. So let's see. We'll have, we do Roman numerals better. Let me know if I have, oh, a bot. Sorry about that. Let me just destroy the bot. I don't know how to pronounce, I don't know how to pronounce your name, Skater. I'm sorry. I've never known. I've seen it 10 times. I've never known how to pronounce it. Please give me like the phonetic spelling. But yes, thank you for stopping by. I'm afraid to, at this point, I'm afraid to ask how to pronounce it, but you know, I'm in learning mode right now. So let's see. We have g of z is equal to x plus cos x hyperbolic cosh y. Do you guys say cosh? Does it annoy your professors? I might say it. I might have to say it. I'm very impulse driven as a person. Y plus, hopefully this will fit. I'm writing a little too big here. Sine x hyperbolic sine y. Okay. So let's rewrite our equations here. Let's see if I can do it from memory, because that'll help me remember it if I can. Is equal to, I'll check after. I'm just going to write them all the way out, and if I'm wrong, I'm wrong. dy, and then we have du dy is equal to negative dv dx. Is that correct? It is. Awesome. I know I just wrote them down, but I think I'll like keep them in my memory if I like write them out from memory. So let's start with this one right here. So we'll have, oops, I want to change the pen, there we go. The derivative with respect to, or the partial with respect to x of the real part of g of z is equal to, that x is going to give us a 1 plus, oh, again, not plus because that cosine is going to contribute a negative, so we'll have 1 minus the sine of x hyperbolic cosine y, and then the partial with respect to y of the imaginary part of g of z is going to be equal to, that y is going to give us a 1, that sine is going to give us a positive cosine x. So right away we can see that this is not going to work. And the hyperbolic function, oh no, it's with respect to y. No. I think it's still positive. I think it's still the same problem but with a different function. So we'll have sine x, and then this is going to give us hyperbolic cosine y, but we still have that plus problem here. That's a no-go. So 2 does not work. Which means we just need to verify 3. Let me check chat again. Gnisma? Bro, is that right? Gnisma Skater? Kosh. You gotta say Kosh. Kosh is just too much fun to say, right? You gotta have fun when you're doing math. Alright, yes, Gnisma Skater. Yes, I told you I've heard it 10 times, but that doesn't mean I remember it. I knew somebody for like 5 years or more. It might have been 6 years, and spent like 2 hours a day with them for 6 years, and then when I saw them once after like a month, I couldn't remember their name. Like, I am awful with names. Although my memory works like this. If I know something, like, I'll know it for the rest of time, or I just don't remember it after 30 seconds. So like, either I'll remember it forever, or I'm never gonna, like, it's just gone. If you tell me like, hey, I'm so-and-so and we're talking conversationally, there's like a 5% chance I'll remember your name. And if I do, I'll just know who you are for the rest of time. But if I don't, good luck. I'm not going to remember. Don't get offended. It's just me. It's not on purpose, I swear. All right, let's go ahead and get this third function knocked out. We're kind of going slow for this stream, but it's relaxing. I'm not stressed yet. Give it some time. Give it some time. This one I have utterly unprepared, but it's not difficult. I like to do. I've been trying to do some of the problems completely unprepared, and some of them prepared. Wow, that made a curve. And then hopefully I can move towards like more completely unprepared as time goes on, because I want to like ease my way into that. But that integral one, like I said, I would have sat here for a million years and never figured it out. I needed lots of outside help for that, which makes me wonder like how I would do it on the GRE. I don't. I guess that like X naught method I could have done. But unless I was allowed a calculator, I'm not even entirely sure how I would have like put a concrete bound on it. Maybe I could have just plugged in values or something. I might be overthinking it. But anyway, let's finish this one here. So we'll have plus I times x squared minus y squared minus x plus z squared. And if I remember correctly, z squared is x plus iy. So we'll probably just substitute that. I say if I remember correctly, that's like definitely what z is equal to. Where z equals x plus iy. So that means z squared is equal to, let's see, we'll just go ahead and write it out as a polynomial. It'll make taking our derivatives easier. Also, that will contribute real and imaginary parts as well. Trying to think how we can group it. Well, let's do this first. So we'll have x squared plus 2ixy minus y squared. I believe that is correct. So we can move our x and y terms. Oh yeah. This isn't too bad. So we can rewrite h of z with that in mind. H of z is going to be equal to y minus y squared minus 2xy plus x squared. And then we can add I times x squared minus y squared minus x plus 2xy. Please let me know if I make a horrific algebra, arithmetic, or calculus mistake. I make no promises. I make no promises. Yo, I can't remember anything. That's my excuse. Gnisma. I might remember that. I'm pouring myself some more water. Sorry if this like looks weird. I've been going to the gym pretty regularly, so I've been trying to keep my water intake high, and it's going really well, actually. I ran for Randolph College when I went there, so since I graduated this spring, and actually a little before that, because cross-country season ended like at the end of fall, I haven't really been exercising, so it's been good to like get out and do it again because, you know, I enjoy it. Okay, got to keep my voice fresh so that I don't falter on you guys. So let's write out those Cauchy-Riemann equations again. Got partial with respect to u, partial with respect to x of u, or the real part, partial with respect to v, partial with respect to y of v, the imaginary part, and partial with respect to u. Oh, this is not good. Partial with respect to y of u, and negative partial with respect to x of v. Okay, so let's start with this one here again, just this first one. I probably should be eyeballing these just to see if it's going to fail, obviously, but I might as well just go through the math, practice some derivatives and stuff. So this will give us partial with respect to x of the real part of h of z. Yeah, but I was, very busy. The reason I stopped running, I could have run spring track and stuff, but I was focusing entirely on math. I prioritized my academics because I wanted to get kind of a graduate level class under my way with that independent study that we did, and that was very rigorous, as well as taking complex analysis at the same time. Wow, this playback, just so you guys know, for my stream is like 30 minutes behind. I'm watching myself do the problem from forever ago. Anyway, let me get back on topic. So this is not very cleanly written, is it? So our y terms here are going to go away, and we'll have negative 2y, the x will go away, plus 2x. Well, that was fairly simple, right? That's the whole real part. Just making sure I'm not missing any terms or anything. I could have missed something somewhere. I believe that's correct. And then we're going to take the partial with respect to y of the imaginary part. So that will give us, let's see, oops, that equal sign is poor. It's very poor. The x term is going to go away, so we'll have minus 2y, so that's the same, and plus 2x. So that one works. And those come from these two terms, respectively. Alrighty, so let me erase that and calculate the second equation. And if we can verify that, we will have our answer. Looking good so far. So partial with respect to y of the real part is going to be equal to, let's see, well, the y is going to be a 1. That's going to be minus 2y minus 2x, and that x is going to go away. And then we'll have partial with respect to x of the imaginary part. And we want that to be negative what we just got. So let's see what we get there. So this is with respect to x. So we will have, let's see, 2x from that x squared term. We'll have minus 1 from the x in the middle. We will have plus 2y, and that is in fact negative what we got here. So that is verified. So our answers are 1 and 3. Now let's see what answer choice that is. That is going to be answer choice D. And reminder, this was problem number 4. We're doing 11. This is taking quite a while, but I guess that number 2 took a while to do. And this one did too, honestly, although it's not that difficult. Okay, that is, yeah, handwriting bad. Okay, so let's move on to the 5th problem, and I will get that up on the screen for you. Also, I think my iPad's time has not gone up since I started streaming. It just says 9:41 forever. It's always 9:41 on the iPad. I don't know how that happened, but it's happened. Alrighty, this is an abstract algebra problem. So let me get this up here. So we have, suppose that R is an integral domain. Moreover, suppose that the ideal generated by the element r squared minus r for all r in big R is equal to the ideal generated by 0. Which of the following hold? So let me get my notes out for this one because abstract algebra is not my strong suit. So let me just write out some definitions to get this one started. So first we have that, this is number 5. We have that R is an integral domain. That is to say, it is a commutative ring with an identity such that we have that if AB is equal to 0, then A equals 0 or B equals 0. That or is the smallest or ever written, and you can't see what I'm writing. You can't see what I'm writing. There you go. It is the smallest or of all time, in case you were wondering. No one can defeat that. Let me see. Alrighty. Yeah. Oh yeah, I forgot to mention complex analysis when you were talking about the courses that you study for math subject. At least for this GRE Prep has complex analysis on it, but I think analysis in general is covered, so I don't know. Really, the lines where you draw math classes are like, it's some of the barriers are blurry. But anyway, so that's the first definition we have, is that R is an integral domain. And we want to suppose that the ideal generated by the element r squared minus r for all r and big R is equal to the ideal generated by 0. So what does that say? Let me see what my notes say about that, actually. Yeah, so let's just write that down mathematically. We have that I subset of R is ideal for all R and R. So what does that mean? Oh yeah, so for ideal that means that for the I in I, we have R times I is in I. Big I. Okay. So now, and then lastly, we have that the ideal generated by the element r squared minus r is equal to the ideal generated by 0. So that means we have that, r squared minus r is equal to the ideal generated by 0, which would just be the set 0. So that means because of that, we can write it as an equality. So I have r squared minus r is equal to 0. And that means that r times r minus 1 is equal to 0. And then we will have that, and we can do this because we're on an integral domain, by the way. That gives us that r equals 0 or 1 for all r and r. And what does that mean? Well, that means that r is equal to, big R is equal to the set 0, 1 or z2. So let's go back to our question here, because we've answered a lot of questions here. Let's get our window capture open. So is R abelian? Is R characteristic 2? Is R a field? Yes. We know all of that from this right here. So the answer is 1, 2, and 3, or E. Alrighty, cool. Cool. All right, so now we can move on to number 6. And I will scroll down to that once in a second. Let's see. Put the iPad down. Yeah, I guess it's easier for me to hold the iPad to do math. I don't know why. Setting it flat on the table just doesn't feel right. Maybe I should get like one of those workstation things that props it up, but I don't really know where I would put it on this desk. So I don't know. My setup is definitely suboptimal for the moment. I might take some time, like a couple hours, to move stuff around and see if I find something better. Excuse me. It's already different from what I started with, like the first setup. This is the second one. The Mark II, if you will. So, I could probably come up with something slightly better. Okay. Do I even need to write anything for this? Let me check my notes and see. Okay, yeah. No, I probably don't need to write anything for this. So We have consider for alpha on the real line the following set. S sub alpha is equal to the ordered pair x, y on R2 such that x squared minus y squared is equal to alpha. And we want to verify the validity of the following three statements: that S sub alpha has two components for alpha greater than or equal to 0, that S sub alpha is symmetric about the y-axis, and that for alpha less than 0, the line y equals 0 is disjoint from S sub alpha. So let's start with the first sentence, or the first statement, sorry, that S sub alpha has two components for I guess for all is a way to read that, for all alpha greater than or equal to 0. And we can see that's not true. If we plug in 0 for alpha, or if we plug in 0, we will not get two values. So if we plug in 0 for alpha and 0 for x and y, we will not get two values. So that does not work there. So next we have, is it symmetric about the y-axis? Well, another way to say that is, do we get the same value if we plug in negative x in place of x? And because we have a square there on our x, that is going to be true. So it is going to be symmetric about the y-axis. And that's very easy to verify out the gate. And 3 might be a little harder to see, but indeed, for all alpha less than or equal to 0, the line y equals 0 is disjoint from S sub alpha. In order for alpha to be less than 0, our x squared will have to be less than our y squared. And that means that we will have a function that never touches the line y equals 0, as we have a strict inequality on that. So that means our answer is 2 and 3, or D in this case. Hopefully I did not deliver that well. Just checking chat real quick, and I'm showing you chat real quick. All right, so next, number 7, we have consider the group with the given presentation. And we want to know what group it is. Sorry for making all of you yawn, likely. So I will go over a quick review of what it's talking about here. Let's see. So we have hold on, let me look at my notes really quickly. Like I said, abstract algebra is not my strong suit. I don't want to say something that's verifiably wrong. What I always tell people is, don't say things that are easy to disprove. If it's hard to disprove, you can say it. But if it's easy to disprove, you shouldn't say it. That's one of my philosophies. Because if it's hard to disprove, you can get away with it for a while. All right, let's see here. So we have that presentation there. Sorry to keep you waiting. Just give me a moment. So we want to take our relations that we've been given for our generators there and simplify them in a way that allows us to kind of identify the group. So we're basically trying to simplify it here, which means we need to do some arithmetic, basically. So let's take our conditions here. Let me get my iPad back up. So we have x, y, x to the negative 1, y to the negative 2 is equal to 1, which is equal to x to the negative 2, y to the negative 1, x. Oops, how did I miss an entire stroke there? xy. Okay, so we are going to take this piece by piece. So we're going to do this on one part and this on another part. So let's start with this one right here. So we're going to clear our inverses there from the right. and that will give us xy is equal to y squared x. And that's very straightforward as to why. And for this one, we will do something similar, and we will get that x, y, rewriting the inequality. Well, I guess it doesn't really matter. Yeah, let's keep it consistent. We'll have that y x squared is equal to x y. That way it's clear that those terms are kind of like multiplied into the one there. Well, now we have two values for this x, y, so we can set those equal to each other. And we'll get that y squared x is equal to y x squared. And from that, we can multiply to get that y is equal to x. And we can plug that back in. So let's plug that into this also. So first of all, this means that we have one generator. That's worth noting, right? Because we're trying to eliminate groups. So this means that we have one generator, we've proven that the two generators, x and y, are in fact the same. So we're going to plug that back into one of our conditions here. So let's see. Let's take the condition x negative 2 y to the negative 1 x y equals 1 and plug in our x there. So then we'll get x to the negative 2 times x to the negative 1 times x equals 1, which will give us, once we cancel these like this, will give us x. Can you still see that? Yes. X to the negative 1 is equal to 1, which implies that x is equal to 1. So we have one generator, and the generator is identity. So we have these two things simultaneously. And when we have these two things simultaneously, we are working with the trivial group. Yeah, I didn't write through my head. Alrighty, so the trivial group is the answer, and that is A for number 7. This is number 7. A. Alrighty, cool. So let us move on to number 8. Let me check chat before I actually move on. How do I get y equals x? So you take your conditions. Oh, well, can you see me? Yeah, okay, good. So you take your two conditions here, and you multiply using 1 until you get two values, or I guess two equations for x equals y. And then I set them equal to each other here and solved. So you just use multiplicative inverses to cancel from both sides until you get y equals x. Does that make sense? Multiply. I can break this into sub-steps, but it's pretty clear. Okay, cool. All right, so let's move on to the next one because I'm going very slow right now, or this stream is taking a while, and I'm hungry. It is 12:30 here, and I've not eaten lunch. So let me show you this problem. So for number 8, we have, suppose you have 2 books on accounting, 2 books on beekeeping, 3 books on chandlering. Does anyone know what chandlering is? Up to the rotation of the circle, how many ways can they be arranged in a circle so that all the books on each topic are together? So the books on each topic have to be together, have to be grouped together, so that already means we're not working with a crazy complicated thing here. So let me sketch this out for you really quickly. So we have, let me get rid of this window. I almost started writing again. All right. So we have, oops, that's the eraser. Up to rotation. Hold on. Let's just draw our circle here real quick. So we have 7. Right, so we'll have book here. I should use the fill-in tool. It'll make this look way nicer. Got a book here. Book here. For those of you who saw my last stream, you know how excited I got for being able to draw stuff. book here. I wonder if I can like select it and copy it so that it's the perfect size. Can I do that? Copy? Oh, I can. Excellent. Okay, so let's do that. How do I like paste it? Paste. Cool. Okay, so we have a book there. Paste a book here. That's going to be the corner of our circle, so to speak. Book here. And a book here at the bottom. Let's keep pasting. This is a very circular circle, I hope you know. This is the most circular circle of all time, just like I drew the tiniest oar of all time. Oh, I also want to preface this by saying if I made any mistakes during this stream, it wasn't my fault, the problem was wrong. That's my official stance on making mathematical mistakes. The problem was wrong. I answered a different problem. It's your job to find what problem I answered. Alright, so those are my attempt at constructing a circle out of squares. So let's see. We have one, what type of book? Yeah, so Chandlering. So we have 2 books on accounting. That is just horrible handwriting. 2 books on beekeeping. And we have 3 on whatever Chandlering is. Okay, so let's see. Up to rotation. Let's just arbitrarily assume that we have, I might need more colors for this, but let's just say that we have our 3 books on Chandlering in these 3 slots. So this will be Chandlering minus the D. Is there a D in that? Yes. So our ways to arrange this are 3 factorial. 3 factorial ways to arrange this, so equals 6. So that's our ways to keep them together, but we can arrange them because we can put, you know, like 1 here, 2 here, 3 here, or 3 there, 1 in the middle, and, you know, all that. So we have 3 factorial ways to arrange those there. And then from there, I didn't really give myself much space to work with here. What color do you guys want? Let's go with purple. So we have these 2. Is there a way for me? I only have 3 on my hotbar, so I guess I'll just go back. Let's do purple and green. Why not? Did I make too many squares? I made way too many squares. This is not accurate. Who's yelling at me in chat because I literally can't count? No one. You should be yelling at me. There's 7 books. How many did I put 8. I put 8. You should be yelling at me right now. This is not correct. Well, if you guys know when I was an intern, the lore, I canonically cannot count, so it's worth mentioning right now. This is the greatest circle of all time. It's about to be. Hold on. This is about to be the best circle of like mankind has ever produced. It's just a triangle. It's fine. It's fine. It's perfect is what I'm saying. So, here we go. Let me switch back to this color here. Okay, so for each of these, we have like subject 1, and subject 2. And so we have these 2 could be swapped, and then these could be swapped, and these could be swapped. So that's 2 times 2 times 2. So we have, so like plus 2 to the 3rd, which is 8. Or it's not plus, it's times. Because we're calculating the total here. Times. So 3 factorial 6 times 2 to the 3rd, which is 8, will give us 6 times 8, which is 48. So we have 48 possible, 48 possible, what's it called, arrangements? 48 possible arrangements. Wow. Wow. I can do better. Oh, that is the best circle of all time. I need some entertainment in my math streams, all right? You know, I'm doing this on purpose, totally Totally not scuffed at all. It's on purpose. All part of my plan. No, my question was 2 subjects of 2 and 1 subject of 3, so that would be 7 books. Does someone want to Google Chandlering and tell me what that is? For the record, I'm still interested. Anyway, so we have 48 possible combinations or arrangements or whatever it's called. Arrangements, so that is 48, so that gives us answer choice D there. All right, cool. Cool. All right, so let's move on to number 9. Like I said, I'm going to just kind of move on. I do want to take time for questions, but I also want to eat food in a timely manner, so I'm going to kind of speed through these last 3. See, I can count the last 3 problems here. So we want to know how many roots are there of, let's write this quartic, we have x to the 4th minus 4x squared minus 8x plus 12 on this range right here. Okay. Alrighty. Get some more water. Hydration is key. I hope if you're following along with me, you are also drinking water with me. Okay. So we have, so let's start by checking out if there's a root on -2, 2 by taking f of -2 and f of 2 and seeing if there's like a sign change. If there's a sign change, then there's obviously at least one root on there. So we have, let's see, what's f of -2? We'll have -2 to the 4th minus 4 times, I'll just write that as 4, and minus, I guess let's write this as plus, just combine some steps to speed up the process, 16 plus 12. -2 to the 4th is going to be 16, right? Yes. That means these are going to cancel out, and that'll leave us with 28, which is greater than 0. And so then if the other one is less than 0, we will know that there is a root on there, at least one. Alrighty, so let's go ahead and plug in f of 2 here. So this is still going to be 16 minus still 16. The sign change doesn't affect those terms at all. So those still die. And then we'll have minus, well, 8 times 2 in this case is going to be minus 16 plus 12. So that is negative. It's equal to -4, which is less than 0. So we know that I write this here, there exists, it's just an E. There exists root on, what's it called, this interval. There's a root on that interval. So we know there's at least one, which allows us to rule out the 0 answer choice. Now we are going to take the derivative of this to see if the behavior of the function elsewhere. So f prime of x is equal to, also we know that there's a root by the IVT, the intermediate value theorem. Just for the record, just in case you were wondering, like, how do you know that? Or how do you know it's continuous? So we have 4x cubed minus 8x minus 8. And that is going to be less than 0. for all x on this interval here. And that's pretty easy to see. I'm just going to claim that, but you can test that out and see that that's pretty clearly. So we know that there are no more roots on that interval because it is monotonically decreasing, and that means it's never going to cross the axis again. So that means that our only root on this interval is going to be the one that's in this, or the one that we verified with the IVT here. So that means there's one root, and that is answer choice B. So let's move on to number 10. Like I said, I'm going to go through these pretty quickly and be a little less thorough for my own sanity. Let me get you number 10 on the board here. So for number 10, we have which integral has the greatest value. So all of these are like easy to evaluate except for cosine squared, but cosine as a function is going to evaluate to be less than 1, or yeah. So because we're squaring something that's less than 1, it's going to be smaller than cosine. So we can already tell that cosine squared is going to be less than cosine, is what I'm saying. So let's evaluate the rest of them, because that is the quote-unquote hard one. And we can do those like in extremely fast fashion. So I'm going to, I haven't calculated all these, but it's probably really, really quick. So the first one is the integral. These are all 0 to pi over 4, so I'm going to omit the bounds after this first one, of sine t dt. Well, that's going to be equal to the negative cosine of t from pi over 4 to 0, or from 0 to pi over 4. Well, the cosine of pi over 4 is going to be square root of 2 over 2, and the cosine is going to be 1. So we'll have negative square root of 2 over 2 minus 1 for that one. So that's going to be quite negative. So we can also write that as 2 square roots of 2 over 2, or negative 2 square roots of 2 over 2, and the 2's cancel, so we'll just have negative root 2 for that one. And the next one is just cosine. So 2, we'll have, let's just skip that, cosine t dt. Well, that's going to be equal to the sine of t from 0 to pi over 4. And that is going to evaluate to be positive, so we already know that it's going to be bigger than cosine. So let's write that, let's evaluate this really quickly. So we'll have sine of pi over 4, which is square root of 2 over 2, and minus sine at 0, which is just 0, so that's square root of 2 over 2. 3 is cosine squared, which we've already said is less than cosine, and we know that sine is bigger than cosine, so that's no problem. So let's do cosine of 2t. So that will give us, sorry, so I guess this is 4, right? The integral of cosine of 2t dt. Well, we can do a super quick u sub here. Let u equal to t, and du is going to equal 2 dt. So we can just take a 1/2 out of that. 1/2 the integral from cos u du, and that will give us 1/2 times the sine of 2t from 0 to pi over 4. And let's see, so if we plug in values for that, that'll give us 1/2 times the sine of, so 2 of pi over 4, so it's pi over 2, so that will be 1, just 1 in there, because the sine of pi over 2 is 1. And then 2 times 0 is still 0, so that will just give us the value of 1/2 here, which is smaller than this one, right? Yeah, because square root of 2 is going to be bigger than 1. So, all right, so let's do the fifth one. I'm just going to erase this here. So the current biggest one is this one right here, number 2. And we will do that. That's going to be 5. And that's the integral, same bounds of sine t cosine t dt. So we can do a u sub here. Let's let u equal sine t, and du is then going to be equal to cosine t dt. So that gives us the following integral of u du, right? Let me check chat, make sure I'm not catastrophically messing up simple calculus. First integral should be +1, not -1. No, it's -1 because you subtract the lower bound. So like the evaluation for cosine is +1, but you're subtracting because of the fundamental theorem of calculus. Let me know if I screwed that up. Chandlering is candle making? That's so cool. Making candles seems like it'd be a chill job. Thanks for the thanks for the intel. Okay, anyway, integral of u du, so that's going to give us 1/2, or I guess u over u squared over 2. And then that's going to equal our u, which is sine. That's going to be sine squared of t over 2, and that's going to be from 0 to pi over 4. So plugging that in, trying to make sure you can see it, we will get, so sine of pi over 4 is square root of 2 over 2. So we'll get square root of 2 over 2 squared. Oh, it's 1/2. That's, okay, so that's, which is equal to 2 over 4 over 2, which is 1/2, which is 1/4. And then that 0 is still going to be 0. So this gives us 1/4, which is smaller than 1/2, which is smaller than this. So the answer choice is 2 here, as this is the biggest one. Square root of 2 over 2 is bigger than 1/2, correct? For anyone who's... There's a negative sign before the cosine. Oh, you're right. That is +1. Okay. So that changes things. Let's see. +1. I don't know if it changes things enough to change it, but that'll give us +2/2, right? So instead of... This is still greater than -1, right? Square root of 2 over 2. Is that greater than? No, that's less than -1. So this is like very slightly positive. But it's still going to be less than this answer choice. But thank you for correcting me on that. I appreciate it. Yeah, it's still the biggest. Okay, cool. If that's +1, this thing is not valid. Yeah, I think negative square root of 2 over 2 is less than -1. But yeah, I think the answer is, anyway. We'll just leave it in that form since there's not really a super easy simplification there. But yeah, so that gives us answer choice of 2, which is B. I wrote this correctly. Yeah, that's B. Okay, last one. Okay, so this one I don't need to write anything for. I just need to tell you some definitions, and I will do that verbally. Okay, so suppose that p of x is a polynomial with non-negative coefficients and even exponents. If a and b are real numbers, what is true about the function f of x equals p of x plus ax plus b? So first of all, you need to know the only thing you need to know here is the definition of concave and convex. I believe in some classes they say concave up and concave down, but that is not like the accepted way to say it. So let me just... I'm sorry. Here, I'm going to drink more water. Anyway, we've got our fancy Google definition here. So the second derivative of a function can be used to determine the concavity of the graph of f. A function whose second derivative is positive will be concave up, which is convex. So there you go. There's your clarifier. So obviously this is always going to be positive. Or rather, the second derivative is always going to be positive because our ax plus b terms are the only ones that are able to have negative coefficients. And if we're taking the second derivative, those terms are going to disappear entirely. So we're always going to have even coefficients and positive coefficients for our even exponents and positive coefficients for our second derivative, which means that for all a and b, f is convex. And that is our answer there. So number 11 is C. So that is our first 11 problems on week 2 knocked out. And so on Friday, hopefully I can start at 11, but that's less likely to happen than I would like. But we will be doing this second 12 on Friday sometime. Look for me between 11 and 1. Like I said, I might try 1 because I don't think we got... Let me check the graph. I haven't been able to verify. Yeah, so, yeah, it hasn't been super active. It looks like we peaked at, well, I guess 22 is not too bad. I thought we had less. But anyway, I might try a little later in the day. It looks like most people came online at 11:30. Well, no, maybe 11 is the right time then. Anyway. So that will complete... Oh, did the stream freeze? Can you guys hear me still? It looks like my face cam froze. Anyway, I'm going to end the stream anyway. But yeah, just look for me on Friday around 11:30 maybe, 11:30. I will try to stream then. If not, it might be closer to 1. It just kind of depends on what I'm doing, but I'll do the second half of the problems. And I will have an example video out for potentially number theory tomorrow. So keep an eye out for that. And if you haven't already, make sure to subscribe. And all of you guys have a great day. Thanks for stopping by. All right, see ya.